We're going to continue talking about ionic compounds today. All fits into our overarching learning goal, which is for both chapters 5 and 6. We're going to focus particularly today on writing chemical formulas and naming ionic compounds that contain more than 2 atoms. Previously, we named binary ionic compounds where you had 2 atoms only. You'd have a metallic cation and a non-metallic anion making an ionic compound. Remember, ionic compounds are formed through the transfer of electrons, and we'll talk more about that at the end of the chapter. Today we're going to name and write chemical formulas for ionic compounds that contain more than 2 atoms. You're still going to have cation, anion, but we're going to introduce polyatomic ions. All right, so we're first going to introduce polyatomic ions. I'm going to show you some tricks of the trade in regard to learning how to name the polyatomic ions, but I will tell you that your polyatomic ions are in the back of your periodic table, so you don't need to memorize them this year. If you don't have your periodic table in front of you, you can grab a green one off my desk. Keep in mind that we also did annotate those periodic tables last time, so make sure that you have yours in front of you where we indicated the charge of silver, cadmium, and zinc, as well as tin and lead. And I may have some extras of those because I wrote it out in multiple class periods if you were out. If not, we'll annotate yours in a little bit. With your polyatomic ions, you're going to have a group of 2 or more covalently bonded atoms that function as a single ion. For example, shown here is hydroxide ion first. With hydroxide ion is OH minus, one of many polyatomic ions. The O and the H are covalently bonded together. We'll get into that in the next chapter. And there is a 1 minus charge over the entire entity. Similarly, a sulfate ion. You have 4 O's covalently bonded to the S with a 2 minus charge overall. I can draw it out, but I think it may be a little bit overwhelming to you, and I don't want to do that at this stage. Drawing these out is not what we're talking about today. We want to be able to name compounds that contain polyatomic ions and write their chemical formulas. So again, you don't need to memorize the polyatomic ions this year. They are provided to you on the back of your periodic table, and you will see those polyatomic ions right here on the screen. For example, acetate ion, CH3COO minus, ammonium ion, NH4 plus. Most of these are anions, but there are a few cations. When we talked about the monatomic anions, such as sulfide ion, oxide ion, phosphide ion, chloride ion, what did they all end in? IDE is correct. What you're seeing here is very few end in IDE. Most of them end in ate and ite. And when they end in ate or ite, they are oxyanions. They contain oxygen. So these are your polyatomic ions. You don't need to memorize them this year, although by the time you do enough formula writing, you'll know most of them anyway. You will need them for college chemistry, AP chemistry, etc. So oxyanions are negative polyatomic ions. Poly means what? Many. so they contain many atoms, more than one. And if it's an oxyanion, it contains oxygen. These will end in ite and ate. The ate will have one more oxygen than ite, but sometimes ite is 3 O's, sometimes ite is 2 O's. So there's no real consistency there. You just need to know them. For example, I'm going to start right here with sulfur. SO3 2 minus, you have 3 O's. This is sulfite ion. SO4 2 minus, so one more O than what you saw previously, is sulfate. Nitrogen, NO2 minus would be a nitrite ion, so it contains N. It's an oxyanion because it contains O. So in this case, the ite form has 2 O's, and that's why I said there's not consistency here. Also, with chlorine and iodine, you get into a situation where it actually has the ability to form 4 oxyanions. And so again, the ite form here has 2 O's. The ate form will always have one more than the ite, so 3 O's. But this has the ability to form 2 additional oxyanions. What does the prefix hypo mean? Think about a hypotonic solution. Less. So with hypo, think about a hypoactive kid. That's somebody who just sits there and doesn't do anything, doesn't move, etc. Hypoglycemia, low blood sugar. Hypo means less than. So in hypochlorite, you have one less O than the ITE form. And in contrast, if you have one more O than the ATE form, we use the prefix per, which is short for hyper. What is a hyperactive child? Somebody who can't stop moving, sit still, etc. Hyperglycemia, high blood sugar, that's diabetes. Hypertonic solutions, more concentrated than what's around. So hypo, one less than the ite form. Hypo can only go with ite. Per, with 8, one more than the 8 form. So hypo is going to have 1 O. Per is going to have 4. And you don't see it all the time. These are where you see it. So I mention it there. Carbonate ion with 3 O's. Phosphite versus phosphate. And again, the 8 form always has one more O than the ite form. Hydrogen can be mixed in to that oxyanion. For example, if you have a phosphate ion, PO4 3 minus, and you throw in a proton, an H plus, you'll take away 1 minus and throw an H in, and you get monohydrogen phosphate ion. Dihydrogen phosphate ion has 2 H's, and your charge has dropped 2. And again, you don't have to memorize these this year. They're given to you, but I want you to see some of the tricks. If you replace within an oxyanion an oxygen with sulfur, you have a thiosulfate ion. So for example here, if you had sulfate, replace one of the O's with an S. Here's thiosulfate ion. I mentioned this one because you'll be using a solution that contains thiosulfate ions in the lab next week. As I've mentioned a few times, your polyatomic ions are on the back of your periodic table. You don't need to memorize them. They will be there for the taking. So this is an oxalate ion, perchlorate ion, permanganate ion. I didn't keep writing ion in here, but you know that when you just have an ion, you have blank ion. You want to be familiar with these. You do not need to memorize. I promise they will always be given to you. What we want to focus on today is naming ionic compounds that contain polyatomic ions, as well as writing their chemical formulas. for the most part, it's easier than what we did the other day. It's more of the same, and there's not much to memorize. The trickiest part is getting those Roman numerals and the naming. So we'll be very, very slow in how we go through this so that you can master it, and I think you will, either by the end of the period today or once you've truly spent a little time with practice. This is the table that's in your notes. I thought it would be easier to work off of it. I can make it a little bit bigger. It's not super dark. Should have bold-faced it. Okay, I'm going to show you how we name here. Pretty straightforward. Ca is calcium. Here's the polyatomic. OH, you don't see the charge in a compound because compounds are electrically neutral, but OH minus is hydroxide. Mg, magnesium, don't confuse it with manganese. And then we've got CO3. CO3 2 minus is a carbonate ion. Here's the carbonate piece. Al for aluminum. Be careful here, you have PO3, and that's phosphite. What would PO4 3 minus be? Phosphate, one more O, good. And very bright class, most of you moving on. You want to try and get a grip on some of this early. It'll be much easier for you in the long run. Ooh, Fe, iron, but iron is a transition element that can form ions of multiple charges, and this was Dora's really good question at the beginning. Let's figure out the charge on iron. We know it can form more than one ion, so we need to specify. What's the charge on a sulfate ion? 2 minus. 3 times 2 is? Divided by 2? Charge on iron in this compound is iron 3 sulfate. That to me is the hardest part. That one's pretty straightforward. The very last one's tricky, but I'm going to show you how to solve it and you'll be very successful with it. Looking at the next one, this looks like I didn't type it correctly. This should have a 3 here, right? Does it have a 3 in your notes? Yes. Yeah. It looks like when I moved it over, I lost it. So in that Google, what I just posted in Google Classroom, we'll need to fix that. All right. So that 3 was there. What's the charge on an oxalate ion? And be careful here. C2O4. What's the charge on oxalate ion? 2 minus. 3 times 2 is 6. Divided by 2 makes the charge on vanadium 3 plus. Vanadium 3 oxalate. Be careful with this. C2O4 2 minus is oxalate ion. That one the kids have trouble with because it doesn't start with a C. This one here is a little bit different. The polyatomic ion is in the front. Look on, well, it's right here. NH4, 1 plus is ammonium. This is a monatomic anion, so it ends in IDE, ammonium sulfide. Let's look at the next set. Na would be sodium. SO3 is sulfite. Back of the periodic table. Look at this one. Ca is calcium. NO3 with a 1 minus charge is nitrate. Al is aluminum. CrO4, 2 minus is chromate. This one's very, very tricky. Copper is in what block of the periodic table? D. It can form ions of multiple charge. We need to figure out which one it is forming in this case. NO2 is what ion with a 1 minus charge? Nitrite is correct. If you don't have parentheses around the polyatomic, it's because you only have one of that polyatomic ion. Your best approach here is to put parentheses in. The charge on nitrite ion is 1 minus. The 2 is inside the parentheses, so you don't use it when figuring out the charge on the copper. You have 1 times 1 is 1. The charge on the copper ion in this case is 1 plus. And this will be copper 1 nitrite. So again, if you don't have parentheses around the polyatomic, put them in if you need to figure out the charge on a cation. You would need to figure out the charge on the cation if you've got tin, lead, and most transition elements. Not group 3, not zinc, not cadmium, not silver, because they only form ions of a one type of charge. This to me is the hardest piece. The rest of it you're going to find pretty easy. Before we go on, I want to make sure you have some practice with it. I don't know if you want to do it together or give these problems a shot. What do you think? You want to try? Go for it. Everybody else's Chromebook is good? Working properly? Alrighty. How we doing? I'm going to start to write some answers in so you can check as you go, and hopefully you'll see you're doing it right. If not, let's figure out what we need to fix. How we doing so far? So far, so good? Okay. And I want to illustrate these for you. How'd we do, and especially with those pesky little Roman numerals? We got it? One of the most important things you'll learn this year, how to write chemical formulas and how to name compounds. I have a cute little project for you to work on at home, and I'll get that out to you next week with ionic and covalent compounds. It's not difficult, it won't take that long, and it's a good learning experience to see what's actually in the foods you eat, the cleaning products you use, medications, etc. Feel pretty good so far? All right, now we're going to work it backward. You know how to name ionic compounds that contain polyatomic ions. Now we want to be able to write the chemical formulas of ionic compounds. This, I think, is the easiest of everything we've done so far. All right. In regard to writing chemical formulas of compounds that contain polyatomic ions, the steps you follow are essentially what we did the other day. They're actually a little easier, but you need parentheses. It says list the chemical symbol and the charge of the cation. It may be polyatomic, but place the atoms with subscripts in parentheses with the charge outside, and I'll illustrate that for you. Same thing for the anion. Then you're going to do what you did previously, swap, drop, reduce, and eliminate. Just be careful that when you reduce, you do not touch any subscript that was part of the original polyatomic ion, because that indicates how many atoms you truly have of that ion. So don't touch those, and I'll illustrate for you. We're going to work through all of these examples here. And I'm going to rework these. The first one is sodium hydroxide. Sodium group 1, 1 plus charge. Polyatomic, I'm going to put in parentheses with the charge on the outside. The 1 goes here, the 1 goes here. You do not include parentheses if the number after the parentheses is 1, as you would have here. You drop the parentheses. The parentheses are necessary when you have more than one of that particular grouping, or in this case, polyatomic ion. Barium chlorate. Barium, group 2, what's its charge? 2 plus. Chlorate, ClO3, 1 minus. The 2 goes here, the 1 goes here, and you have barium chlorate. I kept the parentheses here because the number after the parentheses was not 1. I have 2 chlorate ions. I need 2 of these to balance out the 2 plus charge for electroneutrality. Aluminum in group 13. Aluminum always has what charge? 3 plus. Now aluminum doesn't have a Roman numeral because it's always 3 plus. Don't get Roman numeral happy. Be careful there. Nitrite. N, that says nitrite, right? Yeah. NO2, 1 minus. The 3 goes here. The 1 goes here. And I have aluminum nitrite. Whereas the Roman numeral is so pesky when naming ionic compounds, it's so easy when writing chemical formulas. The Roman numeral 3 is the charge on which ion? The first one, iron. So this is iron 3 ion, that's an E, may not be that clear, sorry. Oxalate C2O4, 2 minus. The 3 goes there, the 2 goes here. And this is the one I was talking about previously. Don't start reducing anything that was initially part of the polyatomic ion. That is an absolute disaster. Be careful there. I'll show you what I mean in reducing in the next one. Okay. The next one's written out as well. You've got chromium. What number is that? 6. Cation first. Phosphite, in parentheses, PO3, 3 minus. So initially, the 6 goes here, the 3 goes here. Can you reduce a 3 and a 6? Yes, to 1 and 2. But I didn't touch that 3 because it's part of the original polyatomic ion. Don't touch it. That is a no-no. That is a disaster. If you start doing that, I'll have you write in different color pencils for the superscripts that become subscripts so you know not to do it. So that reduces to the 1 and the 2 shown here. What's ammonium? First one on there. NH4 with a 1 plus charge. And again, I put my polyatomics in parentheses with the charge outside. Here's another polyatomic, open parentheses. Sulfite is SO3, 2 minus. The 1 goes here, the 2 goes here. I have NH4, what did I forget? The 2. So always go back and look at what you've done so you don't make silly boo-boos like that. And again, I dropped the parentheses off the sulfide ion because I only have 1 of them. All right, lithium phosphate. What's the charge on lithium? 1 plus. Phosphate is PO4 with what charge? 3 minus. The 1 goes there, the 3 goes there. Magnesium oxalate. Magnesium has what charge? 2 plus, group 2. Oxalate we've seen before. 2 minus. What's going to happen to those 2's? They're going to cancel. But I'm not going to touch that 2 or 4 part of the oxalate anion. You try the next 3. I've got them on the screen for you, and I'll write the answers here. Let's see. Should I show you, or are you not quite ready? Show? Okay. The last one is the trickiest. How'd we do? Let me move those over so you can see. How'd we do? How'd we do? All right? One last thing I want to show you just really fits with, and then you're going to have the rest of the period to work on classwork 2-1. You will find practice online if you Google any type of online practice for writing and naming, well, writing chemical formulas and naming ionic compounds. You'll find I had a really good link. It worked last year, but as I said earlier, when I tried it, it did weird things to the computer. So I've deleted it here, and as soon as I can get back on Edline, I will delete it from there as well. If you have that link in your notes, put a line through it. Don't go there. There are really fun little iPad apps too. A lot of them are free, and I'll show you that in the second half for those of you who want to take a look there. Classwork 2.1 you'll be working on in just a few minutes. The last thing I want to mention is how to name and write chemical formulas for hydrates. And we'll get into hydrates a little bit more during the year. We have a cool lab on a hydrate as well. Epsom salts is an example of a hydrate. It's magnesium sulfate heptahydrate. What you find with hydrates is that you have water molecules incorporated into the structure of the ionic compound. Ionic compounds have a certain structure, and we'll take a look at this later on in the chapter, but it looks something like this. I sometimes think about the old-fashioned jungle gyms where you'd have those domes and you used to climb atop them, but they have a structure such as these, and within this structure you can find water molecules, and when you find the water molecules, we refer to these type of ionic compounds as hydrates containing water. Like when you're hydrated, you have a lot of water in your system. When you name them, it's really very easy. If you have, for example, I'll do the chemical formula first. If you're doing the chemical formula first, if you have barium chloride, you know how to write that chemical formula. Then it says dihydrate. You put a dot there. It's usually not that big. I just can't make it much smaller off the program. Di is a prefix that means two, and these prefixes are provided to you on the back of your periodic table. You replace hydrate with water. Calcium nitrate, correctly formula written, and you replace hydrate with water. Tetra, prefix that means four, like tetraploidy, you may or may not remember from genetics. When you heat a hydrated compound, you will drive off all the water, and this is something we'll be doing later in the year. We are going to start with copper 2 sulfate pentahydrate, so 5 water molecules within the crystal lattice. If you heat it, represented by that triangle, you'll get copper 2 sulfate, and the 5 water molecules will go into the environment because they'll be in the gaseous form. This is the hydrate, the ionic compound that contains water in the crystal lattice. When it's without water, we say it's anhydrous material. So an is a prefix that means not, like anomaly, normal versus abnormal. And let's just see if we can name these and write chemical formulas. I think you'll find it to be very straightforward. And let's take a look at that. So what we're looking at here, the first one says strontium iodate. How would we write the chemical formula for strontium iodate? Strontium has what charge? 2 plus iodate. So you have IO3 with a 1 minus charge. So the 2 is going to drop right here. Tri represents what number? 3, H2O. What about aluminum? What's bromate? And then this 3 would come from the aluminum. And how many waters do you have? 4 is correct. How about naming? How would we name this one? Na is sodium, SO3 2 minuses, sulfite, and then 9 would be nana, and H2O is replaced with hydrate. And what about this last one? Mg is ClO3 is 8 is octa, like an octopus has 8 tentacles. Water, hydrate. Pretty straightforward. What you're going to want to do in the second half is classwork 2.1. You can do all of it now. Some of you already did part 1 after your test. If you didn't, you want to make sure you do that. Although I think parts 2 and 3 will better serve you now. All of that should be done for Tuesday, so that when we do oxidation numbers, which the kids do find challenging, you will have a solid understanding of how to write chemical formulas and how to name ionic compounds. You need mastery of this concept by Tuesday. We're going to do oxidation numbers on Tuesday. Next week is running a little bit differently. You're looking at a quiz on this as well as oxidation numbers on Thursday. We'll do a lab on Thursday as well. Please, please, please utilize the remaining of the period, and there's quite a bit of time to work through classwork 2-1.